Hello everyone. Myself Dr. Rajesh Prasad. I am currently working as professor in CSE department at Akgec Ghaziabad. So I am going to talk about parallel algorithms. Yeah. Do we know that why we need parallel? Parallelization is important in algorithms where we are going to deal with heavy amount of data, right? So and we require efficiency also. So let's define algorithm. So an algorithm is, we know that is a sequence of steps that take input from the user and after some computation produces an output, right? So this is algorithm. So of course parallel algorithm is also going to be the part of the algorithm. So, okay, so parallel algorithm is also going to be the algorithm but with some extra features, right? So actually in the parallel algorithm we are going to use multiple processors, right, to divide the task into the several among the several processor. Like see, we have one processor P1, P2, P3. So we can divide the task into the modules like this and this and this, right? And definitely we are going to have different processing devices, right? And second thing is the concurrency and like parallelism. There are two things, concurrency and parallelism. Both seems to be the similar, but there is a bit difference between both. Actually, concurrency is about managing multiple instruction sequences at the same time, okay? While parallelism is running multiple instruction sequences. That means concurrency is about managing and parallelism is about running. There is difference over here. So concurrency like will manage, parallelism will run the multiple instructions at the same time. Both are talking about simultaneous things, right? We might have seen in concurrency like mutual exclusion and critical section problems. Also in this critical section problem or mutual exclusion, we are only managing that if a process is entering into the critical section, no other process is going to allow into the critical section, right? So that concurrency can be achieved. So we are managing over there also, but we are just stopping that, like see, if a process is entering into its critical section, other has to wait, right? So that is what concurrency is all about, okay? But in parallelism we are not like managing, we are just allowing multiple instruction to be executed simultaneously, okay? Yes. So this parallelism is achieved by using multitasking, okay, in the Python, while concurrency is achieved by using threading. So that is the difference over here. So concurrent processing, so this is where we require concurrent processing that can divide a complex task and process it on multiple systems to produce the output in quick time, okay? So concurrent processing is essential where the task involves processing a huge bulk of complex data, right? This is where we require concurrent, like we require parallel algorithm. This is where our need is, okay? For example, suppose we are talking about genomic data set, weather data set, and in my biomedical analysis, where we are interested in handling the huge amount of data. So we cannot handle with sequential algorithms or sequential computer. We have to deploy multiple computer or multiple processors at the same time. So what is parallelism? Okay, so this is actually the process of processing several set of instructions simultaneously, right? It reduces the total computational time. Parallelism can be implemented using parallel computer. We'll say that parallel computers, many computers, those who are connected by the networks, they will be treated as a parallel computer. Sometimes they are sharing the data using the network, sometimes they are sharing the data using the shared memory, right? So shared memory, they can share the data. Like, see, it's very simple concept to achieve the parallelism. Suppose this is processor number 1, this is processor number 2, this is processor number 3, right? So they are going to do some task. Definitely they are going to do some task, right? But so in the parallel algorithms, parallelization, headache is how they are going to communicate. That means when they are done with some computation, this is also done with some computation, this is also done with the computation. So how to combine the solutions obtained by P1, P2, P3? You remember, this P1, P2, P3, they cannot communicate as it is. So they have to communicate via some network, interconnection network, right? This is interconnection network, or they are going to connect with this shared memory. They are going to connect with this shared memory, right? So this is the shared memory or interconnection network. This has to communicate with this, then this is going to communicate, this is going to communicate. I said there is no interconnection among them. They are going to share the information via either shared memory or interconnection network, right? Yeah. So if like, see, that is a computer with many parallel computer require parallel algorithms. Yes. So yeah, so we have seen that algorithm is going to either use sequential computer or going to use parallel computer. Depending on the architecture of computers, we have two types of algorithms. First one is sequential, where only one processor is going to be required, right? So not like many processors, many computer we need. And second is the parallel algorithm, right? Where we require multiple like processors. Those can be running in like parallel, and the result can be combined using the shared memory or interconnection network, right? Yeah. So, but one question is arising over here. Is it like easy to divide a large problem into sub problem? We know that communication, once you divide the problem into like, divide the problem among several processors, communication overhead is coming into the pictures, right? Yeah. So it's hard for them to communicate, and this overhead must be computed while computing the efficiency or computing the total cost of the solutions or computing the total running time of the algorithm. So this is why they are saying that it's not easy to divide a problem into sub-problems. Sub-problems may have data dependency among them. Therefore, the processors have to communicate with each other. As I said that they have to communicate with each other. And it is by the observation that communication overhead is more than communication overhead is more it's not like very small amount, it's like a big amount. So it has been found that time needed by the processor in communicating with each other is more than the actual processing time. This is the observation. So what is solution? To design an algorithm properly, we must have a model, clear-cut model of the computation. So there are 4 types of models, like we know it. So first model is SISD. SISD computers, model of computation. So single instruction, single data. Second one is SIMD, single instruction, multiple data. Third model is multiple instruction, single data. And fourth model of computer is multiple instruction and multiple data, right? Yeah. So let's talk about SISD computers, right? It's like we have only control unit, single control unit, and this is instruction stream, and one processor we have. Here, not like we are not interested in SISD computers. We have only one processor. There is no parallelism over here. And this is memory. Single data stream, memory is going to share. So we cannot achieve the parallelism into the SISD computer. In SIMD computer, single instruction is provided by the control unit. Single instruction is provided by the control unit, and multiple data. Definitely you have, if you have multiple data, so we need multiple processors. See here, we need multiple processor 1, processor 2, 3 up to and so on n. So you know, this is getting data stream from the shared memory or interconnection network, data stream 1, 2 up to and so on. We have multiple data streams. Are you getting my point? Okay. So these are going to communicate via shared memory. In this, we can provide the parallelism. Okay. So this is the model of SIMD computer. And you see here, like if they are going to use shared memory or they are going to use interconnection. If they are going to use shared memory, they are going to be called as parallel processing, right? If they are going like distributed computing, all these clouds, we are using shared memory structure. If they are using like LAN or some interconnection network, they are termed as parallel computers. So that is difference between parallel processing and parallel computers, right? In parallel computers, all the processors, they are going to communicate with each other via interconnection network, while in parallel processing, all these processors, they are going to connect with the shared memory structure. Yeah. So next category is like MISD, multiple instruction single data. Of course, you have multiple control units, instruction are so different, right? And we have single memory. So you know, this data stream is going to be the single. So in this process, like every control unit is given. So question is that are we going to achieve the multi-processing here? Are we going to achieve, because data streams, so how they are going to communicate is the question over here. Communication among the processors is going to be a question over here, right? So this kind of processor, so best process parallel processing can be achieved by this, like SIMD, or MIMD. Yeah, next is MIMD category. See, so this is where you can get multiple instructions, multiple control unit, and you have shared memory and interconnection network. This is the model of the parallel algorithm and parallel computer. This is where we are going to talk about, right? Multiple instruction, so multiple data. So but this is not going to provide the parallelism, because data stream is not, like communication will be an issue. This, however, this can provide the parallelism, this cannot provide the parallelism. Okay. So question is that how to analyze the parallel algorithms, right? So you see, parallel algorithms are designed to improve the computational speed of a computer. It's clear. For analyzing a parallel algorithms, we have the following parameters. First one is the time complexity. As we have been discussing in the we have been discussing in the sequential processing. Second is the total number of processors used. Definitely we are going to account the total number of processors. This is one of the factor. And time complexity, as we have been using in sequential computer, is going to be the same. So total cost of deploying the multiple processors, right? So this is how we are going to compute the analyze the parallel algorithm. So another parameter is speed of and total cost. Let's have one example. See, speed up. So what is speed up? You know, speed up of parallel algorithm is like T1 by TP. What is T1? T1 is the time taken by sequential processing divided by TP is time taken by the parallel processing, right? So this is the fraction. This is what it is given. Is like this defined as the ratio of the worst case execution time of the fastest known sequential algorithm for the same problem to the worst case, right? execution time of the parallel algorithm. So that is the speed up, right? Speed up is always sequential time divided by parallel time. And then what is total cost is like time complexity times number of processors used, right? So this is the total cost. Next parameter is going to be efficiency, worst case execution time of sequential algorithm. Here divide by worst case execution time of the parallel algorithm. So can you see the difference between S and E, speed up and efficiency? Yes, speed up is like the ratio of the worst case execution time of the fastest known sequential algorithm. Okay, is like you have to check the fastest known, while efficiency is not going to talk about fastest known, worst case execution time of sequential algorithm. So let's define the mathematical formula for this. So speed up is going to be defined by T1 by Tp. T1 is time taken by sequential processing. Tp is time taken by the parallel processing. This is the T1 and by Tp. This is known as speed up of a parallel algorithms, right? Yeah. Second is efficiency. Efficiency is going to be defined by speed up by number of processors. P is the number of processors. And you can see that speed up is T1 by Tp. And this is P. Efficiency is T1 by Tp. Then this is P. So that is going to be efficiency. And important law concerning the parallel algorithms is Amdahl law. So what is this? Speed up is limited. Speed up of any parallel algorithm is limited by 1 upon f plus 1 minus f by p. What is f? F is fraction of the problem which can be solved in sequential time. Actually, F is the fraction. You know that any algorithm cannot be 100% parallel, because suppose you have algorithm like a processor like this P1 and this is processor P2. This is another processor P3, right? So if you have multiple processor, although they are like working in parallel, but still we need them to combine once they are sharing. So once we are combining the solution, so definitely sequential task is going to be into the picture. So not like any problem cannot be 100% parallel, right? So that is why this they are talking about fraction of the problem which can be solved in the sequential time. Let's have the example. Suppose T1 is 100 seconds. That means the problem can be solved in 100-second time taken with one processor, right? And F is 0.2. That means 20% of task is sequential. As I said that no any task can be 100% parallel. You cannot get any task which can be solved in 100% parallel time, right? And second is F, like see this 20% of task is it's sequential, or you can say that 80% task is going to be the parallel. 80% is parallel. Yes, of course. So like see, and assume that you have 4 number of processors, right? So what is TP? Question is that how to compute TP? TP is, you see here, TP is nothing, S equal to T1 by TP, right? Yes. And what is S? S is equal to 1 upon F plus 1 minus F upon P. So from here, you can see that TP is nothing but T1 by S. And compute value of S from here, because we are given S. So if you see this, S equal to 1 upon F, F is 0.2. That means 20% of the task is sequential. So 0.2 plus 1 minus 0.2, number of processors are 4, right? Yes. So this is going to be, S is going to be S equal to 1 upon 0.2 plus 0.8 by 4. This is the value of S. And if you get this S and put here, so Tp will be T1 by S. So answer from this is going to be the 40 seconds. See, T1 was 100, so and 100 divide by this value, so you are going to get Tp as 100 second. So time taken by parallel processing is going to be 100 second. So if you see the computational speed is T1 by Tp. So speed up is T1 and T1 is 100 divided by 40. So you know this is going to be 2.5. That means by using parallel processing, your speed was multiplied by 2.5. Clear? Yeah. So that means parallel processing was beneficial over here. So, okay. So what is efficiency? Efficiency is calculated by time taken by sequential processing divided by number of processors. So what is time taken by sequential processing? It is 2.5. Number of processors are 4. So efficiency is going to be 62.4%. Definitely efficiency is calculated in the percentage, right? Yeah, so this is efficiency in parallel. So what will be the total cost? If you see, if you want to compute the total cost, just like you have calculated TP is 40. So total cost 4 processor into 4, right? So total cost will be 160 millisecond or second depending on the time. So this is time, second. So this is going to be second. Here total cost, we are not interested in money, we are interested in total time actually. So total time after applying these processors is going to be 140 seconds. So this is the computation for total cost. Yeah. So next important concept is performance measurement of parallel algorithm. So first we are done. This is a very important concept, how to measure the performance of parallel algorithms, right? So first one we have seen the speed up T1 by Tp, yes, and efficiency we have seen that like time taken by parallel divided by number of processor. Total cost we have seen that P into Tp, that is the second total. Scalability, you know, that is very important. Parallel algorithm, they are very scalable, right? So you know, so at least we are not going to deploy multiple processors, other interfaces. So only you have to use multiple processor, rest interfaces can be the same. So this scalability can be of two types: strong scalability, weak scalability. Fix the problem in strong scalability, fix the problem size and increase the number of processors, right? Yeah, problem size is fixed, you are increasing the number of processors. So this is strong scaling. Weak scaling, as the demand like arise, increase the problem size proportionally to the number of processors. Like, you know, if you are increasing the processor, problem size should also be increased, right? Yeah. So this is the fourth parameter, scalability. And we know that parallel overhead is also important task. Once you are like adding the processors, overhead is also going to be one of the important tasks, right? So how to define the overhead? This is the formula for parallel overhead. P into time taken by parallel processing minus time taken by the sequential processors. And I introduced already this MDAL is very important when you are talking about parallel processing. So this is 1 upon F plus 1 minus F divided by P. Remember, F is the fraction of the problem which is going to be sequential. You know, same formula can be converted into the another way, that if parallel percentage is given, right? Then another one is the Gustafson's law. This is the sequential processing, yeah, that problem size in parallel algorithm ka change. Yeah, so this is saying that if you increase the problem size, parallel algorithm will give better, and this is this formula for computing the speed up. P minus 1 minus f into P. Remember, f is still the time which is going to be like calculated if you are using this sequential processing. So in the next lecture, we'll talk about parallel algorithms model. So I'm ending over here. So next, you can watch my next recording in order to understand the parallel computing models, right? So these are the references. Thomas Corman, Saroj Sahni. This is the important book which is totally focusing on the design and analysis of parallel algorithms. Thank you.